Okay, thank you, Duccio, and hello, everybody. I am Matilde Signorini, and I'm an astrophysicist. So what I'm going to do is give you, in this half an hour, I hope, a little bit of an introduction to the cosmological problem that we wanted to address using neural network. And I'll start from the basics, and I hope to convince you that the problem is meaningful. And then Lorenzo will take over and discuss the actual machine learning techniques that we used. So the context is that of cosmology. So from the very beginning, what is cosmology? Is the study of the large-scale properties of the universe as a whole. And so the kind of questions that we want to ask are those like, what does the universe come from? What is it made of? And what are its physical properties? And how do they evolve eventually with time? A way to study the universe is to study its expansion history. So I guess everyone knows here that the universe is expanding, and also that this expansion is actually accelerating in the last billion years or so. And so by studying this expansion history, let's say, I'll show you how we can get meaningful information about the physics of our universe. So I'll start with some assumptions. The literature is full of works in which these assumptions are discussed, but I will take them for granted here. And so these are that, well, the first one is the cosmological principle. So we are an average observer, a random observer in the universe, and any other observer would come to the same conclusion as us in another part of the universe. The second thing is that the universe is homogeneous, isotropic, and it is expanding. We can prove that on large scale, it is homogeneous and isotropic. I will now focus a little bit on why we know it is expanding, because it is needed to introduce the concept of redshift, of which you will hear a lot this morning. So if we look at galaxies at large distances from us, we observe their spectra, and we see that their spectra are redshifted. So the emission lines are shifted toward higher wavelengths than the one we expect them to be. We see that this is happening for all the galaxies, and this is also what another observer would observe in another part of the universe. This means that the galaxies are moving away from us, and this is why their wavelengths are redshifted, so they become larger. And this is happening everywhere, so it means that the universe as a whole is expanding. So this is what we call the cosmological redshift. So it is the amount of which the spectrum is shifted. And of course, if we there is a relation between the redshift and the time. So the light that was emitted at earlier epochs, we see it more redshifted than the objects which emitted closer to us. So going back to the assumptions, if we take these assumptions, we can describe this space-time with a certain metric, which is the Friedman-Lemaitre-Robertson-Walker metric, which is a long name, but it's quite simple. It's the one I'm showing you here. The important thing to know is that to describe this space-time in which we're living in, we need this scale factor, A of t, which is the quantity that has inside all the information about the expansion of the universe. So this formula is general, so this could be a universe which is expanding or collapsing in very different possible ways. But so the thing is, everything about its expansion is inside this factor. This factor has a relation with the redshift. So actually, the redshift of an object is telling us what the scale factor, so the expansion of the universe, was at the moment of its emission. So another assumption is that Einstein's field equations are true. And if we take this for granted, we can combine the metric I was showing with the field equation and derive these two equations here, which are called Friedman's equations. And you can see that they are describing the evolution of the scale factor of the universe. So they describe the derivatives. And the important thing to notice is that the quantities which are inside these equations, so they are, well, physical constant, but also the density and the pressure of the components of the universe. So the thing is, the components of the universe are telling it how to expand. And the fact that the universe is expanding is also influencing the density of the components themselves. You also know the presence of this lambda factor. Now, probably everyone knows or maybe not, depending on your background, that this lambda is something that Einstein added to the field equations in order for them to be able to describe a stationary universe, because he didn't know that the universe was expanding. We know now that it is expanding, but this lambda factor is needed still nowadays because we saw that the expansion is actually accelerating. So this lambda accounts for something that we call dark energy, and that we have no very clear idea what it is, but it is a component of the universe that implies a repulsive force between the components. So talking about these components of the universe, in the standard cosmology framework, we can say that, well, for every component, we can write the equation of state that relates the pressure and the density. And depending on the component, we will have a different parameter W. I'm showing you that here because it's something also that Lorenzo will discuss about. So this W is the coefficients that relates the pressure with the density. Given this, we can also find how the density of a component changes with the expansion of the universe. And so you see that depending on the value of this W, we have a different evolution of the density with the expansion of the universe itself. So the components that we can have are the pressureless matter, and for this W is 0, and so its density goes with the scale factor to the -3, which is what we expect. I mean, as the volume of the universe is increasing, the density goes down. We can have radiation, which has a W of 1/3, and so the decline is a bit faster. And then we have this repulsive force. Now, in the standard cosmological model, the lambda CDM scenario, this repulsive force is a component which has a constant density with time. So this dark energy has a constant density, and this means that its W must be exactly -1. So a bit more about this standard cosmological model. It's called lambda CDM because we account for this lambda, so this dark energy, and we have dark matter, and this dark matter is cold. So we have matter which is not baryonic, and it is not relativistic. Given this pi of the universe in this model, we have that, well, we can describe the presence of matter and dark energy with these density parameters. But the thing here is that matter is around 30% of the universe, and dark energy accounts for the other 70%. That's the important thing to know. And also, that this universe must be geometrically flat. So this is the standard scenario in which we're moving in. And it's the standard model because it's a model which, well, explains a lot of the observations that we have in cosmology. And it needs quite a small number of free parameters to explain everything. So that's why, well, many people very much like it. But there are some tension between observation and these standard cosmological models. I will not go into detail here, but probably the most famous one, I don't know if any of you have ever heard of, is the H-Naught tension. Now, H-Naught is the current expansion rate of the universe. And while the prediction for this number is something around 70, I forgot to put the this is for kilometers per second per megaparsec. It's a velocity. I apologize for the, I forgot the measurements here. And so the prediction is around 67, while the local measurements with supernovae 1A gives us a value of 74. And you see that the discrepancy in terms of sigmas is very high. There are other tensions that I will not discuss here, but so the thing is, this model is working well. It explains a lot of things of how the structure in the universe are formed, but there are some tensions around. This explains also why people started to, yes. W is the coefficient of the equation of state for, here for dark matter. So it has to be -1. So we must have that the pressure is -ρ. And so if we want the dark energy to have a constant density with time, you see that the density goes as the scale factor to -3 1 plus W. So this W must be -1 if you want this to be constant. So this is in the standard model. And Other extensions of this model, the easiest ones are those in which this parameter W is not exactly -1. And for example, we have a WCDM model in which still we have a repulsive force, but its value is different from -1. Or we can have CPL model, these are a class of models in which these can vary with the redshift. So the dark energy changes with time, but there are a lot of possible alternative model. I'm showing these two here also because Lorenzo will then discuss how we use some of them. Yeah. I mean, this comes from, I'm not an expert on this, but I would say this is just the simplest way you can extend the Lambda CDM model. So, I mean, there are observations that tend in this direction. That's why they also have been proposed. There are things that show that dark energy may be increasing with time, but this not come with an exact physical description of what dark energy is and why it must go in this way. Yeah. So you see, after all of this, that the way in which the universe is expanding depends on the properties of the components of the universe. So by observing this expansion history, we can derive information about the physics, which is what we want to do. Here. We do not directly observe the derivatives of the scale factor, but we can have observations that things that we can observe that depend on it. There are many ways to do so. The things that we did was to use the luminosity distance redshift relation. Now, if we have an astrophysical object which has an intrinsic luminosity L, on Earth we do not observe it, we observe its flux, and the relation between the flux and the intrinsic luminosity depends on this thing called the luminosity distance. With the assumption we have made at the beginning, we can write it in this way. And so it depends on the redshift of the object we are observing. And it also depends on the cosmological model. So the way in which the universe is made and it expands made it different the way we observe a flux of an object with a given intrinsic luminosity. In particular, here you can see this h of z. Before I discuss the h naught, which is the current expansion rate, in general, h is the expansion rate at a given time or at a given redshift. So you can see it written here. And so on the free parameters are these h naught, this omega matter, and this w, which is the dark energy W I was showing earlier. So in a lambda CDM standard model, this is -1, so this thing cancels out. But if we assume another shape for this W, we can have a different luminosity distance redshift relation. So our goal is to have objects for which we know both the redshift and the distance luminosity to build what we call the Hubble diagram, and to use it to constrain the cosmological model that is underlying it. Now, to do so, we need objects for which we know the luminosity distance, sorry. And these objects, we obviously need objects for which we know the luminosity distance without having any cosmological assumptions. So we need objects which are standard candles. If we have a standard candle, it means that we observe the flux, we know the intrinsic luminosity in some other way, and so we can derive the luminosity distance. The most famous standard candles are Supernovae 1a, probably everyone has heard of them, but just to, a Supernovae 1a happen when we have a white dwarf and a companion star. The companion star accretes its mass into the white dwarf, and when it reaches this mass limit, it collapses and explodes. As the physical limit for the explosion of these objects is always the same for all the objects, it means that the luminosity they produce is always the same. So we can derive their distance. We also can observe their redshift by observing their spectra, which is the easiest part here. Given this, we can build this, which is the Hubble diagram of supernovae. And so you see we have many objects for which we know the redshift, and we can measure this luminosity distance in this way. So the shape of this diagram depends on how the universe is made. So actually, this Hubble diagram of supernovae was what allowed us to prove that the expansion of the universe is accelerating. So this shape is not consistent with a uniform which is expanding all the same rate, but is consistent with a universe which instead has an accelerated expansion now. However, you see the supernovae arrive at redshift. We have them up to redshift 1.5, maybe up to 2, but with very few objects here. What does it mean? That we can use them to investigate the universe up to when it was 6 billion years old, let's say. So the first 6 billion years of the expansion history cannot be investigated with these objects. We, of course, would like to also see build this Hubble diagram at higher redshift, so investigating earlier cosmic times. And we can do so using quasars, which are the other objects that we have used in our work together with supernovae. Very briefly, what is a quasar? We know that at the center of galaxies, we have supermassive black holes, which means black holes where the mass is around hundreds or even thousands of billions of solar masses. We can have an active galactic nucleus with this supermassive black hole, so we can have an accretion disk where gas falls into the black hole, and in doing so, it loses its gravitational energy, it heats up, and it emits light. This process is very efficient, and so the emission of this central region of the galaxy can be more than the whole emission of the host galaxy. When this happens, we usually call these objects quasars. So they're the most luminous persistent sources that we have in the universe, and this means also that we can observe them up to very far. Actually, now we observe them to up to when the universe was less than a giga-year old. So they're good in our goal to proving the expansion history at earlier times. And also we know a lot of them, which is also something important because, of course, if you only have one point in this diagram, it doesn't have much information. The sad news is that the emission of quasar is not standard. So its luminosity can vary up to many orders of magnitude. So by simply observing its flux, we cannot determine its luminosity distance. However, they can be standardized. This is the happy news, thanks to an observational result, which is the nonlinear relation between the X-ray and the UV luminosity in quasars. So quasars emit at very many different wavelengths. If we take their X-ray and UV luminosity, there is this relation, which is obviously linear in the logarithmic scale. You can see it here as the log of X-ray luminosity over the UV one. And so the thing is, this coefficient gamma is different from 1, is around 0.6. And so what does it happen? If I take the flux luminosity relation and I substitute here for the luminosities, the luminosity distance is always the same if we observe in the X or in the UV. And so we can get an equation for the luminosity distance of a quasar by only observing its fluxes and knowing the parameters of the relation. So these objects can be standardized and we can derive distances for them. This means we can build a, I'm sorry, there's something wrong with this was supposed to be full of yellow points. Why? Something happened. Okay, I'm sorry, but yeah, okay. Imagine that here there is a lot of yellow points. So the thing is, cyan points here are supernovae 1A. The ghost yellow points here, which I'm not showing, are quasars. But the important thing is that this red dot, likely we have them. This is the average for the, here we have distance modulus instead of the luminosity distance, but it's the same thing. These are the average values for quasars in small redshift beams. So you see here we have supernovae, these are quasars, and you see that we can extend quite a bit this Hubble diagram. And we can go to when the universe was around 1 billion year old. So this is a quite significant extension. And also you can note that in the common redshift range, there is a perfect match between supernovae and quasars. This is also reassuring us that the method that we're using is working, but you should trust quasars. So if we extend this Hubble diagram, we can now use it to test cosmological models, as I was saying at the beginning. And there are many ways to do this. One way is that of well, assume a cosmological model and then use the data to constrain its parameters. Now, before I show you the WCDM and CPL models, now you see why they were useful. But this is simply to show a work which we recently published, where the main author is Giada Bargiacchi, and in which we tested different cosmological models with supernovae, quasars, and also BAO, which is another kind of cosmological probe. Don't mind it. I'm sorry, but I only had these plots with also BAOs. The important thing here is that if we assume a model, we assume a shape for the W of dark energy, which was inside of this equation. And for example, here we say that W is a constant, but that can vary. And what we get here, the green points are the prediction for the lambda CDM model. So you see here, for example, that in the lambda CDM model, we have W, which is -1, and omega matter, which is 0.3. This is the density of matter in the universe. And so if we look at the contour, which is the blue one for supernovae and quasar, this point is a little more than 3 sigma distance. If we take another model, for example, the CPL, we have two spaces because the parameters here are free, are WA, W naught, and omega matter. But the important thing here is that in this region, we see that the prediction of lambda CDM touches the 3 sigma line. Here, it is at around a 4 sigma tension. So two important things. The first is that when we use quasars, and so we test the Hubble diagram at high redshift, there is a significant tension with the prediction of the flat lambda CDM model.
We use neural networks in order to solve this problem. I will try to tell you how and maybe why also. And we also use some kind of statistical tests in order to find out also to be quantitative in terms of discrimination of the real data with respect to from a model. So let's start with what has already been done. And basically, one of the major tools that was already used were the Gaussian processes. With the Gaussian processes, there were lots of problems in terms that, I mean, I have to be sincere. Eventually, we understood that the problems were not really connected to the Gaussian processes, but in literature, what was kind of evident maybe is that there were problems regarding stability using the methods that were shown. And also there were huge errors in predicting the shape of the function W, which was the one that Matilde was speaking about before, when using their models. Actually, the plots looks like that. So what I'm showing you here is basically the function WZ, which is exactly the W that is very important in order to predict which is the distance luminosity. And these are the results that other groups, I mean, this is one result, but others were fairly similar, obtained using as a prediction, so schematizing basically the function WZ with the Gaussian processes. Now, as you can see, the variance is pretty high in the sense that up to, I mean, 0.5, there is some kind of stability, but then there is a huge spread in error. So this is something very, very annoying in the sense that for the cosmologists, they really wanted to have something kind of, narrow and to bound correctly the function. But here there is something that's not going on pretty correctly. Yeah? Yeah. This is not our work, but I think that they did this. I'm asking for the help of the cosmologist. I think.
Yes.
Okay, so this was what was the process. So they come to our office and say, okay, we have this problem, and they use these tools. What do you know? We answer saying, well, we know a little bit of neural networks. So unfortunately, we cannot understand all the process with Gaussian processes, but we know a little bit of them. So why don't use them? And in the following, I try to explain you the whole process. Our goal basically was to obtain something at the very beginning, was to obtain something better than this, of course. Okay, but actually, we said, let's try and let's begin with something a little bit easy. So let's not fit the real data, but let's start with the simulated data. And so we said, let's try to understand if WZ is the right function. I mean, let's see if it behaves correctly, if there are any problems in the inversion, who knows. And so this is the steps we followed. We start fixing the functional form of W with very simple ones at the very beginning. And then we generated optimal data in the sense that they were very dense in terms of the Hubble diagram. So the plot I showed before, there were lots of points, more than the one you were able to observe. And then we try to fit with existing procedures, not with the Gaussian processes, but with parametric procedures like a polynomial fit, and also with neural networks. So we fit the Hubble diagram with the neural network, and then we inverted the basically starting from the distance luminosity you could infer from your fit using derivatives and lots of very boring calculations. You arrive at an expression for W. And we couldn't retrieve the real function that we inserted. So this is something that was a little bit concerning at the very beginning, because it's the end. I mean, finish, we cannot go on. Because we weren't able to retrieve the real function, even with very simple one, like, for example, the lambda CDM one, so the W equal to -1. Our guess, I mean, there were two, of course, a line of reasoning. One was that basically we were doing things wrong, but we checked them a lot. We checked the calculation and so on and so forth. And so we said, maybe there is some kind of numerical problems going on. And so our guess was that there was a lot of numerical instability, maybe, or mathematical instability. And as I will try to show you, this, I think, is the case for the other literature. So we decided to shift to the level above of WZ, which is the E of Z, which is nothing but the integral function that was at the exponent. I will show you, of course, another time later. But it was basically the level before. Another tool that was very useful for cosmologists. Of course, it is not as important to them as W, but it's connected to W and it's still relevant. So we said, okay, let's shift to I of Z, which is another function in the form of the distance luminosity that was showing to you before. So, of course, we said, okay, we will fit a nonlinear model using that. We are we are no more interested in retrieving WZ. We are only interested in analyzing the form of I of Z. So we shift our attention to that, and we say, we don't care. We will, yeah. Yeah, exactly. But I said that I mean, you're corresponding with the derivative. Formally, yes, but we assume that the problem was numerical somehow, or with the inversion of the problem. This was our guess, let's say. So people started from, in the literature, correct me if I'm wrong, people start from regressing this, basically, and then invert and arrive there. We started here with I of Z and fit this. Basically, schematizing I of Z with a neural network. So this was the framework. It's different from what they have already been tried, and this was our guess at the very first time. And at the very beginning, we didn't see actually lots of, I mean, to us, it was some kind of a matter of choice. We said, why don't do that? In principle, we didn't saw nothing very strange. So we started the regression. And so our problem was starting with Z as a variable, so the redshift, with Y, which in theory should be DL, so the distance luminosity, so basically the Y portion of the Hubble diagram, we change it a little bit in order to make the regression a little bit simpler with just the transformation. We obtain another y, but it's just a matter of simplifications. And then we adjusted consequently the errors delta y on the points on the Hubble diagram, the one that were already shown you before. So this was our setting. So we wanted to, in the end, we arrive at this connection between our non-parametric model, I mean, non-parametric, of course, in a sense that with lots of degrees of freedom, let me rephrase it in this way, which is I and n of z, and then the connection, so the thing we want to predict is this, is y. And the link between them is this functional, this integral functional here. So we fed both inside a loss function, so I, n, which is our function, and the prediction, I, which of course is a nonlinear functional of the I and n, and the error was simply the square error weighted by the statistical error of the data. So this is the setting. Now, if everything is clear, if you're with me, let me continue and let me tell you which were our goals. Our goals are, first of all, try to find a reliable procedure to fit this I and n. So we wanted to test everything to be sure that this way of reasoning has no faults and so on and so forth. Then we want to understand why people got the results that they got. So, for example, we want to understand why still Lambda CDM was using Supernovae, quite a relevant model, and also why people got their very big errors using W. Those were our goals. And in the end, of course, we want to try at least, and I hope that you will give me a feedback on that. We want to be quantitative in terms of difference between the results of our regression and the distance of the result of our regression to the actual Lambda CDM model. So those were our goals. So let's start with the first one, which is try to find a reliable fit procedure of the integral function. So test if everything is defined correctly, if there are any bugs, and so on and so forth. Those are the steps we followed. We started by saying we will regress I of z with a neural network. And here I'm kind of assuming that everybody more or less know what a neural network is and what this implies. If there are, of course, any questions, we can discuss them later, or if you want a clarification. For those of you who doesn't know what a neural network is, basically a neural network is just a very fancy and very powerful way of parameterizing the way you explore the function space. So we decided to use this way of parameterizing, this way of exploring the function space, the neural network. You could also use Gaussian processes even with this task, so not exactly in the way they were already being used, but you can also use them there. But unfortunately, we were not very expert on that. You can also use other very fancy stuff, like, for example, also, yeah, even kernels, I think, are used, something we already discussed yesterday, lots of different ways. Now, and then what really matters, I think, in our results is the procedure we use. We started fixing I of z and omega m, which were two important parameters in our functional, so in the way we link the neural network with the actual prediction, so with the actual, let's say, point on the Hubble diagram. We fix them, and then we generate data with increasing complexity. So we generate several Hubble diagrams with increasing complexity, and then I will try to explain you what does increasing complexity mean in this context. And then we fit with the neural network. So we fit I of z, so we set up a fitting procedure, so a loss minimization, basically, using our neural network. And we use the loss as a proxy. So between our several realization of datas, we had a problem of hyperparameter optimization. So we wanted to understand which are the best width and depth of our neural network, which are the best learning rates, which are the best batch size, and so on and so forth. Lots of different hyperparameters that according to us, were very relevant. For example, a problem that was immediate at this point due to the connection between the integral function and the prediction was how to do the integral. I mean, because we wanted to implement this on GPU, so we had problems with that. We decided to do this numerically. And of course, what we found was that the steps at which you compute the integral was very important. So really a huge work in terms of hyperparameter optimization. And we use as a data pot the simulated data with different models. So in the end, we want to have a single algorithm, so with everything fixed, all the hyperparameter fixed, and then these should be tested with other mock samples that were not used, of course, to parameterize everything. And we wanted to know if it works or not. So we want to retrieve everything, so the IZ that we wanted to, that we fixed at the beginning. So this was our procedure, yeah? We sampling from a model, which is the one we fixed. So this everything here, in this whole process, there are no real data, of course. So we keep them in another hard drive, let's say. We didn't check them, and we said, and of course, we know them, but they weren't used in this process. It was, of course, a key part of the whole fit procedure. So we fix the model. So we fix I of Z, and then we fixed on omega m. Actually, omega m was the same for everything, and then we changed I of Z. And then we said, okay, we want to be able to fit this with an indicator, which was the loss of the fit at the end. So the square, with the weighted square loss I showed you before. So no real data here. There is a Python package for generating random data according to a model and according to a distribution of Z. So there are lots of very fancy tools that we used in order to be able to have those mock data samples. Okay. So in the end, we decided to test them against Lambda CDM, which was, in the back of our mind, our most important model, let's say, and also with a particular CPL model, just to be able to say, okay, we're not only able to fit very well Lambda CDM, but also other models, which were of course different from the one we used to train everything. So the models we used were Lambda CDM and CPL. CPL was the one before. So with CPL model, you fix the W form, so W of Z, and with the fixed W of Z, you can derive the integral. And with the integral, you can generate the data, and with the generated data, and then we feed the generated data. This was our process. And we use different WA, and we use WB connected to WA in this way. So if you remember, in the CPL model, the functional form of WZ was fixed. There were two main parameters, WA and WB. We generate them. We started using different settings. And this is not, unfortunately, I mean, the process was quite long because also we changed the data size and the distribution. So we change the distribution of Z. We start with basically a perfect sample, so more than 6,000 different points evenly distributed on Z. So basically, just to be practical, what we did is changing the complexity of the fit. So in principle, when if you have a very easy fit, is then when you have lots of points, very precise. But then you can start having less points, not evenly distributed, with bigger error, and so on and so forth. And those are the degrees of freedom we change with our mock data samples. So then we also change our errors, and our errors were basically perfect, so basically 0. And then we raised the complexity. Of course, with 0, there were numerical instability, but we fixed them. And then we raise our errors up to the realistic ones. And then we also tried something a little bit more than the realistic ones. In all those settings, we wanted to be able to retrieve the proper integral of Z. I'm stressing that a lot because, I mean, I found that it was very, very hard to convince people that you've done things right in these settings. I mean, it was very, very, very strange to me at the very beginning, but it's very, I mean, I come from a completely different field, let's say, area, and I found it's pretty delicate field, it's pretty tough to convince people here. So So, yeah, cosmology is a very, very precise. So those are our assumptions. Those were our assumptions. What does it mean? It means that first of all we have to. Oh, sorry. Yeah, yeah. Sorry.
The errors of the data.
Yeah.
Then model we get is relation between uncertainties that indirect redshift or so.
Yeah, yeah, they were accounted.
The modeling of the data errors is known and is like fully implemented.
Ah, okay. Actually, okay, I tell you the way. Yeah, yeah. Yeah, of course, at low Z you have smaller errors, at higher Z you have bigger errors. Yeah, I think so. I mean, in the procedure, actually, we took as a reference the real data order of magnitude errors, and then we basically changed the size of errors according to the distribution of Z from 0 to that. So there is a dependence on the error size with Z, and this is something we account for. But I mean, if I have understood what I've done, basically we didn't account for if the data X as an error, then data X plus 1 as another one, for example. This was not accounted. But I personally, at the moment, don't. I don't see why it should be like that, because when they were independent observations. So I don't. Maybe it's the observer that. Yeah, that might be. Yeah, that might be. We didn't account for that. We didn't account for that. No, you can answer. Okay. If you want, you can answer to everybody loudly. Okay. So those were the ways in which we generate our data. Now, the first step is connect the integral function, so I and n, to the prediction, so the point. And this was done using, as I told you, this functional here. And this functional here is an integral. And numerically, it's kind of a little bit of a problem doing that, because we wanted to do everything on GPUs due to, of course, speed problems. And this is the way we've done this. We basically segmented the portion that Z until, for every data, until Z of I, which is the redshift of the point you want to predict, the Y, so or the distance luminosity. So for each data, we have a redshift. We generated basically segmentation, an array of different steps from 0 to the redshift of the data, and the steps at the end was fixed with this value here, so 5 times 10 to the minus 4. Then for each of them, in order to the whole process has to work in this way. You give me Z, and then I give you Y. So you give me Z, I compute this array here from 0 to Z. Then for each point, I compute I and n of kz, which is here. So we segmented this thing. Then we do that for everything. We applied nonlinear function, and then we sum. This is the way we computed the integral. Regarding omega m, we want to be, which is the trivial way, okay? We wanted to compute to be a little bit independent with respect to omega m. So we said, let's try different omega m during our process agnostically. So in our procedure, we will do different fit for different omega m's. And indeed, we want to be slightly independent of omega m. So we varied basically omega m in 3 steps. So in the end, there were lots of fit, because each one for every setting, one for every omega m we wanted to test. So very, very boring stuff. Unfortunately, it was done in parallel numerically. And I and n, of course, was a neural network, which is on a hyperparameters. Those are basically the hyperparameters we fixed. So the hyperbolic tangent as a nonlinear function, a linear function at the end, and then 20 neurons, 20 hidden neurons, and 4 hidden layers. With this setting here, it was everything implemented numerically with this tool, which is a very nice one. I recommend you. It's free. It's called the Hyperparameter Optimization Tool by Tune. It's called. And it's very flexible to me because you can use it also for problems that are not connected with neural networks or with predictions or with machine learning. You can parallelize everything. And everything was parallelized on GPUs and on multiple GPUs because we were pretty lucky. It was a server just arrived at our university, so we were able to exploit it. So those are the tool we use for all the hyperparameter optimization and simulations. And then we do everything as parallel as it was possible because the amount of fees were huge. For every fitting procedure in the end has those hyperparameters. Okay. Now we wanted also to define an error, and this might be a delicate point. We wanted to define an error at for each prediction. And the way we define the error of our prediction, we're using the Bootstrap Sampling, so the Bootstrap method, which is it's not that difficult in terms of, it's not, I mean, it's quite intuitive maybe. You start having a sample, and then you sample without remission a fixed number of data, of points. No, you sample with remission, so you could also sample multiple times, a fixed number of data, and then until you arrive at the same size of the beginning data set. So, for example, you have 5 balls. You sample them with remission, so you could also sample twice 5 balls. And so, for each of them, we did a fitting procedure. So, we generate our mock data sample, we generate our bootstrap sample, then we fit the integral function, and in the end, we obtain I and n and the prediction, so the distance modulus, let's say. This was done for every fixed amount of time. In this case, is b equals to 50. So after that, we compute the standard deviation and for the integral function and for the prediction, so for the distance modulus. So to sum up, in the end, we were able, for a given mock data sample, and also for the real one and so on, to obtain a prediction with a variance, with an error, and then an integral function, again, with an error. Now, those are the results we obtain. I will show you, first of all, the results for the perfect data. So those are other data we generated. We generated a perfect Lambda CDM model, which is this one, and a perfect CPL model, which is this one. As you can see, I mean, the minimum of the loss is with 0.3. Here there is a sub-figure which shows you that actually there is just a scale, and we were able to retrieve basically perfectly the Lambda CDM or the CPL function. So when we saw this, we were pretty reassured. So, okay, everything is working right. But then we tried with data which were of the same, of course, we also with mock data samples, which were again a Lambda CDM and a CPL model, but in the range and with the redshift distribution of the real supernovae. So the real data has, of course, a redshift distribution and an errors. We choose exactly the same error, the same redshift distribution and the same errors, basically. And we generated, according to a Lambda CDM model and a CPL model, our mock data sample, and we fit them. And the Lambda CDM model looks pretty fine, but the CPL model, we couldn't able to retrieve the correct one. And it was a little bit discouraging at the very first after all the time, because we said, okay, it doesn't work. I mean, here it says that the best result of this fit is this, and with a very, very small, with an omega m, which is not exactly the one we generated data with. So we were a little bit concerned. And again, there were two things. Actually, after that, there was a lot of trial and error. Again, we said, oh my God, everything is the end, or there might be errors in the code, so lots of debug. But everything seems to work fine. And actually, we had the idea to investigate again the properties of the relation we want to fit. And this might be a delicate thing. So be with me and try to follow me, because this is the way we try to address why this happens. Yeah? Oh, yeah, you're sure. Yeah, you're right. So here, those are the results. Here is the integral function. And here is the prediction. So the Hubble diagram is this one here. And here is the corresponding integral function we have fitted. With the dotted line, you see what you see is the underlying model. So the model that was used to generate the mock data samples. So here is lambda CDM, as you can see, it's 0 everywhere. And here is the CPL model, which has this behavior here. So it's not 0 as the integral function has another behavior. And those are the realization for different omega m, because as I was saying you, we tried different omega m as a hyperparameter for each fit, and we picked the omega m with the smallest loss function. So here, the omega m with the smallest loss function is 0.3. So here you should check the green one, which is basically in line with the lambda CDM model, inside, let's say, the bound of the error. And this is the corresponding prediction in the Hubble diagram, because remember, there is this connection between the integral function and the distance luminosity according to the integral. So those are connected, and this is the result, how this integral function reverberates on the Hubble diagram. And here is the same for the CPL model. Here, as you can see, you should pick the 0.2 according to your loss function, which is basically, again, very much like a lambda CDM model, again, which was the thing that actually rang the bell. And here, it fits quite correctly the data, but somehow it's not the right one, because we generated them according to a CPL model. So this was something a little bit strange, because visually it's not that bad, the result on the prediction. Why? And here everything seems to work perfectly. With the perfect data, everything seems to work perfectly. But with the supernovae, we had this problem. Now we started to understand why. Basically, why is that happening? And so this was very much the second point, because actually, we started to understand why people may always fit lambda CDM using supernovae, which is basically what happens in the literature. Yeah? Yeah. Oh, if for the fit, yeah. Yeah. It's true, but actually, with the perfect data, we were able to find the right one with the ideal data set. So the one with loss of points. This is just the thing I'm showing you is the problem with the supernovae. So we were pretty reassured with the perfect data side. But anyway, we didn't use regularization because we weren't very much afraid of overfitting here, actually. And also we used stochastic optimizers. Of course, we use ADAM, which is maybe lots of you have already heard of it. It's an adaptive stochastic gradient descent, but it's kind of the standard when it comes to neural network. So the procedure was, I mean, the network is expressive enough to capture those very simple functions. We are pretty sure about that. Also because, yeah. Mm-hmm. Yeah, you're right. But if that was the case, we should have overfit our data. Yeah, but you're right. But actually, this might be a whole different talk. This is a problem with neural networks, right? Because you start going bigger, and with basically every task, you have an amount of parameters which are more than the number of data. Yeah, I mean, but that's I mean, as far as I know, this is a problem. The very cool thing is that these things don't happen very frequently with neural networks sometimes. For example, you always have a loss of free parameters. There are some explications for that. For example, a very interesting one to me is the regularization, the loss of implicit regularization you get changing the shape of your INN. With hyperbolic tangent activation function, as far as I know, which are bounded functions, if you go, for example, if you grow in depth enough, you find that there is some kind of implicit regularization due to the depth of the model. And this is something that is basically something that bounds the way you can explore your the space of functions. There are also lots of implicit regularization that comes, for example, with the optimizer, because the adaptive gradient descent also tries to avoid basically lots of very strange situation in terms of exploring the loss functions. But again, if overfit would have been the problem, I had the feeling that this was not the set, those were not the results. So we should have always, I mean, at least with this context, with very simple stuff like that, in principle, we should have saw something like an indication of the overfitting procedure. So what I will try to explain you here is that there is a mathematical problem why we cannot do that. It's not due to the the unbalance between the expressivity of our neural network and the data set. So we can do this. Let me continue one slide, not two slides. And if this doesn't convince you, then we can again discuss about the overfitting problem. If you that you don't. Okay. Actually, with the calibration stuff, we've also tried with regularization, but nothing changed. It wasn't a problem. I think that, and this was something that I think it's worth for the workshop, might be a very nice thing to discuss, because still here the neural network is some kind of is inside a model, let's say. And so that might be another thing that avoids the overfitting problem. This was one of my feelings, let's say. Yeah? Yeah. Oh, no, of course, this is the ensemble with the Bootstrap. Yeah, I am. Of course, yeah. That's an important point. Yeah, I'm smoothing out some. I'm using TensorFlow. Oh, yeah. Okay. So with PyTorch, it's automatically included. Okay. Okay, I saw that with the TensorFlow variables, basically you can decide to regularize them, but in this procedure here we choose to not do this. So let's try to address this problem now. So why we cannot fit the supernovae data? So the question we asked was, how is our prediction sensitive with respect to a given model, so a given shape of the function? And then we said, okay, let's try a variation of the prediction, so on the Hubble diagram, and try to connect the variation on the Hubble diagram with the variation on the function INN. This was our goal. And we thought about the functional derivative. So we said, a prediction on the Hubble diagram is linked to a local prediction on the function space of the integral by this formula here. You can compute this, and you have to evaluate it somewhere. And we decided to evaluate this in the Lambda CDM model, because we kind of had basically with the supernovae, we always feed the Lambda CDM model. So we said, what's going on here? So we compute the functional derivative. We evaluate it in the Lambda CDM model, which means INN equals 0. And then we try to approximate the deviation of our prediction with respect to a Lambda CDM model. If you do the calculation, you can link the variation on the Hubble diagram, let's say on the distance luminosity, with respect to a variation on the space of the integral. And this is evaluated at a Lambda CDM model. So this is nothing but the difference between our INN and the lambda CDM model. But again, lambda CDM model, as Matilda was saying, is 0. So this is nothing but INN in our case. So this is something we could plot and analyze. And if we do this, we obtain this plot here. So we plot here not the discrepance, but exactly the functional derivative evaluated at lambda CDM. So then you should also, if you want to understand the variation, you should also put inside the variation with respect to lambda CDM. This is not done here. This is just the functional derivative. So basically, this whole function here evaluated at this function here evaluated at I equals 0, which is the lambda CDM model. And we obtain this plot. And this plot is quite interesting to us because if you look carefully, the functional derivative is very small here in the first, or at least compared to its whole variation, is very small in the first redshift region. So we had the feeling that the first data, so the first part of the redshift distribution is not relevant. It's not relevant in the prediction, at least in this context. So actually, it's basically the way that the space of function we fit and the prediction space are linked that somehow bounds the way you explore the functional space, because it's, I don't know, maybe just a fancy way of saying that, but it's somehow how the gradient flows through from the output through your to your neural network, that is kind of multiplied by this if you are around a lambda CDM model. And so it means that you have to be very careful in terms of saying, oh, I'm fitting these things here if you are doing something which is connected with the integral, because the way those two spaces are coupled is very strange. And yeah.
So is this just a way to say that takes a lot of the difference between the data and this?
Precisely. That's the thing. And this is why basically quasars are very important, but not quasars, but everything that's at high redshift, which is something, even if you think about it, I mean, when I saw this, when I plot this, my laptop said, I mean, it's quite natural. I mean, it's very difficult to get things very far, so of course they are more important. It's always like that. So, actually, the supernovae dataset is basically localized here, whereas the quasars extends all here up to z equals 6. So this is why we think the supernovae part is not very relevant. And indeed, then we added quasars. So then we added, what I will show you now is everything with quasars. And everything with quasars is this plot here. So this is the Hubble diagram with also the quasars data inside. So again, mock data. And this is so simulated data. And this is again the same for lambda CDM model and a CPL model. Here it's the lambda CDM fit, which is exactly that. And here is the CPL model, which is exactly that. Again, very important is that we fix every hyperparameters. So it's not that we again optimize everything, otherwise it would be like cheating. So we fix everything, and it's the same algorithm that runs here and here. And again, we were able to retrieve the proper omega m of our data, and we obtained that. So now we say, okay, quasars are very important to discriminate models because they extend up to high redshift, and this is due to the coupling between the function you want to fit and the space where all the data naturally lives, so the input one. So you are interested in a physical quantity which is a little bit far from the real data, and this is the coupling is very tricky, at least if you come from a lambda CDM context, if you come from a lambda CDM point of view. So yeah. So the left one, sorry, oh yeah, they are exactly the same. The difference is the underlying model. On the left, it's the lambda CDM. So data were generated assuming the integral function equal to 0. And here, so those data here were generated according to the integral function equal to a function of z, which is the CPL one. Fixing now WA, so a free parameter, it has been fixed. Again, here you got the INN, so the result of the average across, every bootstrap sample of your data. This was a very important point I forgot to mention. Thank you. The average of them with the standard deviation. And we, again, as a remark, we also checked that everything was going on correctly. We try we plot the histograms and the median and so on to check whether it was really a Gaussian. So during the bootstrap procedure, which is always a nice one of the way you can understand if everything is working correctly. And yeah, sorry.
So it seems that only the models like the models with omega and
This is because the data were generated with 0.3, and this is I think it's a kind of little bit weakness of the whole procedure. Inside the omega m, there was the right one. Inside of the omega m, we search, but we also tested going a little bit closer with here. And of course, the trend is the one you say you look. So we decided to put them. But in the training procedure and also in the test I will show you in a moment, we only changed across 3 different omega m due to computational resources. Yeah. Yeah, omega is a hyperparameter. Okay, let me rephrase in this way. Each of that is a whole fitting procedure, each point here. Every time I fit again, but I run with a different hyperparameter omega m. So the red one is the result of the omega m equal 2. Here is the corresponding prediction, and this is the loss function with omega m equal 2. Again, same thing, omega m equal 3. I get exactly the lambda CDM1, which was generated with omega m equal 3. Then I get this plot here, and then I arrive here. And the same for omega m 0.4. Yeah.
You're always interpolating your model. But if you do bootstraps, you know, and the ones at some point, the majority of the bootstraps will be extrapolated
from the left.
You see, because if you do bootstraps, I mean, it's the majority of them will extrapolate it for, I don't know, see the
I don't know if I'm getting right this. Why are you saying that? Because if I look at that, I am a bit concerned about always sampling in the region of small z. Why are you saying IO? Mm-hmm. Mm-hmm.
And if you look at all points are always extrapolated, then you would start some of them, majority of them, will be concentrated closely. And then when you model, the high values will be extrapolating to the region.
Oh, yeah. You mean I see your point. I mean you will extrapolate all the high Z region. Yeah. This is a thing that how can I say? This is true, but actually it's intrinsic to the problem somehow, right? And if I have to be sincere, right? If you put the how can I say? I mean, really, those data here, okay, the lambda CDM points here, and those are, I mean, those ways here are the ones that are very important. I mean, you cannot how can I say? It's inside the problem. So I mean, it's true that this is something we thought a little bit about that, but at the time we weren't able to address properly how should we compensate that, maybe with a weighted bootstrap, maybe with a different integral. Yeah.
Just vary the points according to the errors that are bootstrapping. That is random exact numbers for each data point that follow
Okay, I thought about that, but in my head, maybe it's wrong, but in my head, it's basically what you are considering when you are weighting it using the weighted loss function. If you're weighting with the square root, you're assuming that they are as a Gaussian distributed around the mean, and you weight them accordingly to that. So you, in principle, you should get the same result as doing it multiple times with a simple square loss, right? If you generate data according to a Gaussian, and then you do multiple fits and you average them, the result, I think, should be exactly like using one, but weighting, using the same mean, but weighting them accordingly to the... You don't get the uncertainty? So you mean that each... Yeah.
Unless we just do it by using the sort of analytical expansion around the medium of the loss function, then if you don't do that, you will use just measure and see what happens to the results, like reading the analysis, right?
Yeah, I'm changing basically the data set each time. Yeah. Mm-hmm. Doing this, okay. Okay. So, okay, I see. Mm-hmm. Okay, I see it. Yeah. Yeah, you know, yeah, that's nice. Yeah, that's nice test. Mm-hmm. Yeah, that's nice test. I think we will try this. That's nice, nice thing. Yeah. Mm-hmm.
It was very similar to something that people are doing for functions.
I was sure. No. I imagined that there were lots of similar, because when you do the talk, I said.
These are used.
Mm-hmm.
And then, yeah.
Okay.
Way between different functions with a set of one-dimensional functions. So that's very complicated way, fast and current collect data.
Mm-hmm.
Okay, and so it looks very similar that we can make a regression on the shape of this function parameterized by neural networks using data that use basically those in terms of simulation. So it's a complicated thing. And this question of the way in which they assess the uncertainties is
with that.
Okay. They remove data from the experimental uncertainty, and then people discuss whether or not this is actually the line.
Okay.
But you should have a...
Yeah. Thank you.
And so what they do at the end is that they have an example of
they generate
a particular example.
All the functions. Yeah.
So it's
Okay. Thank you very much. So it's called a reconstruction of pattern distribution and PDF. Okay. Not... Okay. Thank you. So at the end, those are the results with real data. Again, we didn't want to have like the statement that this is how the real integral function works. Of course, the main goal was to basically try to exclude lambda CDM in a kind of robust way, and have some kind of indication of how the real data, the real integral function is. And basically, those are the fit we got. So with the same algorithm again, same hyperparameters, we get those results here. Again, we varied omega m, 0.2, 0.3, and 0.4. And the best one is with the 0.2, so the red one here, which is very far from the lambda CDM one. And also here, again, this is the fit. So the red curve here is the result of the fit on the space of the prediction, so on the Hubble diagram. And as you can see, it fits quite well, I mean, visually, and it's very far from the real integral one. And here is a remark that I think it should be relevant, is that, as you can see, the errors are quite big here compared to the one we got in the old, in the data I was showing you. And I don't know, we kind of had the feeling that the real data were very far from the very different from the distribution we trained our data on. This was one of the feeling we had while watching at this graph here, this chart here. So we said, it should be like, we should quantify how much this result here, so 0.2 here with that, is different from a 0.3 omega m and lambda CDM model, which is the one that is assumed, let's say, one of the most relevant candidates of those data. And this is the way we try to be quantitative in that. And this is another very important procedure I think I would like to discuss with you. So in order to be quantitative, we try to think in this way. We wanted to rule out the lambda CDM model, and so we proceed saying we have to be strictly in terms of what we want to rule out. And we said lambda CDM omega m equals 0.3 is 0.301, something like that. So I'm saying that, but I'll write down 0.3. Then we said we can generate as many data as we wanted. So this is another thing we can do, because we have the whole package. We can generate data according to the redshift distribution, and we want to exploit that. And then we want to test how everything works with respect to the statistics of our data, so to the errors of our data. And we had the feeling further we were, a little bit hyped about the functional derivative stuff. We wanted to take it into account also as well. And we came up with this idea to define an observable, which I will call a delta lambda CDM. And delta lambda CDM works as follows. We generate a mock data sample of lambda CDM model, again, same procedure as before, with omega m, and the error were increasing. So we have lots of different data samples with increasing errors. And then we estimate this indicator here, delta omega m, with, again, its error. And we assume that each of these procedures is independent, in the sense that we expect this indicator here to be distributed as a Gaussian. Which is the indicator? The indicator will be a scalar, and that this scalar will be compared with the result with the real data. So we have mock data samples and real one, and we want to compare those two things. And in the end, the indicator is basically this one. So let me try to express you the idea behind this, and you will maybe give me feedback or your impressions. The idea is that if you deviate on average from the lambda CDM model with something that is compared with the prediction error you have, then you cannot rule out lambda CDM. So if this thing here, if you are far from your underlying model, so the model you want to rule out, of an amount that on average is on the order of the variance of your prediction, you cannot rule out the model. Again, how much you have to weight the way you are far is also taking into account how your prediction is coupled with the distance modulus. So the weight is basically the functional derivative. So we say we will weight more a deviation at high redshift, and weight less a deviation at low redshift. This is because at low redshift, every model looks the same. But at high redshift, you have very different models that produce very different data. So if this delta is around is less than 1, then you cannot rule out lambda CDM models from your mock data sample or from your real data sample. If it's more than 1, then there is a strong suggestion that your data are not lambda CDM model. Again, we varied omega m in the same way as before, and those are the results. So those are only a portion of them because otherwise it would have been boring, but those are the results for the error going from an average of 0.12 to 0.15, which doesn't mean kind of nothing, saying like that, but to give you an idea, data were around 0.14. Okay, so from here I'm showing you a little bit less and a little bit more. Of course, we checked up to 0, and up to 0 everything was fine. So though this is our indicator, so the delta lambda CDM I will show you for mock data samples, so simulated ones, with mean and average. And as you can see, it's always between 0 and 1, which is cool because it means that we cannot rule out lambda CDM from our mock data samples. And now, another important thing, this is the part where Z is less than 2. So we evaluate up to 2 and plot the average here and with the standard deviation. Then this is the same from 2 to the end of our redshift distribution. And again, it's around 0 and 1. So even in that region, you cannot rule out lambda CDM. And this is the result of, I think each point is the result of 90 simulations, 30 per omega m. So 30, 39. And those are the results for the real data. So of the best fit procedure I show you in the this indicator evaluated exactly using, of course, it's a dot because it's one realization because of the real data. And as you can see, it's very close to 1. So with Z less than 2, really the deviation weighted according to the functional derivative are not as, I mean, does not explain a difference with the lambda CDM model. But with Z over than 2, it's here. So very, very far, up to 5 sigmas on this distribution here from lambda CDM model. So this is basically our indicator that the data at high redshift are very, very different. And I hope that I have convinced you with this procedure. I'm happy to discuss about that. And to sum up our result is that neural networks are, I mean, looks very useful tool in cosmology. They're not the only one. There are lots of them. And of course, we hope to have a kind of plausible form from our EA of Z, which for someone who has a cosmological background, which is not me, I've heard that it's like an interacting dark sector model, which means that basically there is correct me if I'm wrong, but the amount of dark matter and the baryonic matter changed across Z, right? It's not fixed.
I mean, it's consistent with dark matter becoming dark energy.
With dark matter, okay.
But even the assumption we made at the beginning, so you can perhaps change general relativity and everything will change. So you can choose where in the assumption list to say that there's something wrong. So if you say everything is correct up to now, but the function of the dark energy is not the correct one, then the function we get is consistent with dark matter becoming dark energy with time. What does it mean if you want dark matter and dark energy?
It's a debate. Yeah.
Yes.
It looks like that, exactly.
Yeah, also interpretation.
While so take the envelope of this cosmological model, take that model the envelope of all the parameters, how much significant you get less than. So you were saying that you have a 4 sigma monster in one.
Yes, for the CPL model. Here
and this benefit model that we're studying now is included the tools that you had in your slide. It's 1 point.
I don't think so. But
yeah, but one thing you will say now that the possible explanation of this tension in the model, right? Okay, I would want to know whether this specific model inside the class
I don't think it's a CPL model, right? It's not. It's not. It's not inside the class of the CPL models. Yeah, so it's not included.
It's not even in the simplest extent of the one that we're showing.
And now we have whether there is now a larger parametric family of models with its interpretation that contains that point.
Oh, yeah, which are the interactive second.
Okay, and those models are much.
So this is consistent with.
We didn't check that. We didn't check. Yeah, working in that regime, no, it's not something we have done. Yeah. If you say this is.
The interactive second models, which are, they can be somehow exotic, but they are based on, physical assumptions. They are not very logical. Those would be in agreement. So if we use this type of model, in this method, we will have the orange point.
But there are other specific models. So yeah, you can find one.
And I hope that I've convinced that this workflow, maybe with some adjustment, can be a very useful one to rule out cosmological models. This is one of our hope, let's say. And of course, but this is something that it's not, we're not the first saying that supernovae are not enough. You also need quasars, so you have to extend our data. This is basically a very profound and fundamental thing, I think, that there is inside this problem. So thank you very much again. And of course, Lambda CDM, not exactly. Maybe we should think about other stuff. If you want, then we can discuss together. And thank you very much again. Messages. Yeah.
Okay, so can you go back like a couple of slides?
Yeah. Those here. There's one.
Like to me, when you read on the Y, it seems like whatever function I observe
is good. Yeah.
Yeah, because it's nice. But basically,
Oh, okay. Yeah. Remember that. Yeah. A little remark here. Those are the real data. If I would have plotted here the corresponding simulated data, one on top of each other, generated with a Lambda CDM model, those data will be like that. So more up. So yeah. No. Yeah. It's just that I put the wrong bottom. Okay. So.
Yeah, no, my point is that when you get the real data, whatever I observe you want.
Yeah, inside certain bounds. Somehow, yeah, somehow inside certain bounds. And the thing is that Lambda CDM is not inside those bounds. But I believe I mean, I'm with you with this point that if I'm sure that if I change more like omega m, or then I will get still a nice fit. So there is lots of uncertainty, at least with these experimental errors, I think. Yeah.
So the fact that your student data not would be that
those are real data. Remember, sorry, not those. I think we're not on the same page, because our simulated data or of course, when we simulate them according to Lambda CDM, we were able to retrieve Lambda CDM perfectly. The thing is that the real data don't seem at all like Lambda CDM model. So the point is that oh, okay. So okay. I think that how can I answer this question? I mean, with the simulation. Oh, okay. I mean, in terms of how much I trust the simulation, I would say a lot, because there is a cosmological package used exactly for simulating cosmological data, and we use that. But and with the same distribution as real data.
Perfect data was okay, 6,000 points with no error, but then when we go to the simulated data we showed earlier, it's the same distribution as supernovae. So we simulate the same supernovae, but with the model, and if we simulate them with Lambda CDM, it's like taking the real data, we refine Lambda CDM.
Because the data are not Lambda CDM, basically. Oh, if you want to answer, I mean.
This is with real data, same procedure, the regression, and we are.
I think I understood now the point. The point is that the majority of the real Lambda CDM data points are with supernovae. Those are with quasars. So the reason why there is this, I mean, someone would say, but why is that anyone has already shown that, has already saw that? Because if the real data are very, I mean, are supposed to be very Lambda CDM data, then, I mean, everything here is wrong. But when I say real data, the majority of the analysis, like the one I've showed you at the very beginning, is done with supernovae. So the thing is that supernovae, as I've tried to show you using the functional derivative argument, always tell you that the data are Lambda CDM. That's the problem, that in the way you parameterize the coupling between the integral function and the distance luminosity, so in the way you parameterizing your model, the relations that there is between your model and the data, you have an implicit bias towards Lambda CDM model. This could be somehow the wrap up of the thing. And this is due to, this is why people fit Lambda CDM model with supernovae. And also we fitted Lambda CDM with real data supernovae. I'm not showing you that here, but we also fit with supernovae Lambda CDM data. So we were in agreement with them. But our point here is that this is not the right data set, because even if there are there are no like the majority of the data are in the low redshift region, but there are few of them in the high redshift that you can obtain with quasar. You have to use them, because otherwise what you're doing is adds lots of biases. I mean, you are in the wrong region. It's yeah. We did with maybe I should have stressed that more. The simulations that we use to train our model, that we use to calibrate our model, our hyperparameters of the fitting procedure, are that. So we used Lambda CDM data and CPL data with different parameters defining the model, ideal data, supernovae, and quasars. Of course, we use supernovae, and this is kind of wrong, supernovae plus quasars. So we also use supernovae to balance everything, and data with zero optimal up to realistic and a little bit more than the realistic one. So in our hyperparameter optimization procedure, we also taken into account that we want to fit very well the supernovae data. The thing is that when they are Lambda CDM, we could fit them very well. So when we simulate supernovae Lambda CDM data, we could fit very well. And this is, for example, and this is an example of that here. As you can see, if I show you that, those are realistic supernovae data, simulated, of course. This is the best loss. The omega m 0.3 is this, and the dotted, oh yeah, maybe I should do that. And the dotted line is the integral you should expect. So I mean, it's well fitted. It's a nice fit. You get a lambda CDM model with the supernovae. The thing is that you also get a lambda CDM model when you generate CPL model, CPL supernovae. And even with visual inspection, they are not that different. I mean, if you look at them, they are not that different, those data, but those are different models and very different ones also, because the CPL model with these parameters is, in terms of cosmological feature, very different from lambda CDM one. But yeah. It's very different from the lambda CDM one. So it means that the way you couple your model, the theoretical model, with the observation has bias towards basically, I mean, it's not expressive in the low redshift region. Because you say, and this is something I tried, because at the very first I had to understand properly how everything was working. And I said, let's assume that our model is a parabola. So like INN is a parabola with diverging, like with very strange behaviors. And the generated data were not very different, not that different with respect to something generated with everything that is flat. And why? Because of the way because of the coupling between the integral function and the prediction. So in the way with the assumption Matilda was saying, so Einstein's field equations are true, you will live in a flat irrotational invariant universe, you end up with a functional relation between the cosmologically relevant parameters W or I, or the integral I and N, with the real data that is a little bit strange in the sense that at load Z there is no difference between different scenarios, but at high Z you will get lots of difference. Yeah. Yeah.
I mean, I want to express part of what you already said from, let's say, point of view of cosmology. Okay. Because it's something that the whole cosmological community is slow to understand. I mean, the basic point here is that everything is highly degenerate at low redshift. And then you can distinguish between classes of models when you go to much higher redshift. And this is something that we are starting to do now. Until 2 years ago, all the cosmological data were at low redshift apart from this. And so that's what's happening. That's why we are doing this kind of analysis now, because we have new data were available before. But the thing which was and is hard to understand is that this result, so that when you are with the high redshift data, then you can obtain all these, you can break this degeneracy. It's counterintuitive from a physical point of view. Because the dark energy component dominates the dynamics of the expansion of the universe at low redshift, simply because at high redshift the volume of the universe was much smaller, and so of course the matter dominates there because of gravity. And so at very high redshift, from a dynamical point of view, the dark energy component is almost irrelevant. It's only the matter which decides the dynamics.
Mm-hmm.
Yet, what we are finding now is that even if the dynamics of the universe is dominated by dark energy and low redshift, the way this happens is highly degenerate among different things. And so, having a lot of data at low redshift, which is where the dark energy is more important, in terms of overall contribution, doesn't have to distinguish which is the right class of model. Instead, when you extend to high redshift and you compare the high and low redshift, even if in the high redshift part, the contribution of the dark energy component is small, is a small fraction, but there is a big difference among different models, and then it's better to see there if you want to distinguish and break the difference. This was something that one would have expected. I mean, for many years, we have said that, okay, we want to understand the Tension component better and break the degeneracy. We have to add more data to the Redshift.
Yeah. Yeah.
So building on the plot of the Robertson that you showed, the yellow and green, sort of echoed what you're saying, how comet cells a lot of density in small redshifts. But this is just the Lambda Factor. If you do this with your CPR model, you get the same flatness at low redshift. And this
yeah, in principle, I think an improvement should be to do this for every class of model that you have that you want to rule out, and this is what I think future work or expansion, the direction future expansion should go. Here, we want to say, if we want to find and to fit lambda CDM, we are champion at it. So if we don't fit that with real data, it's a problem. Okay, that's why I'm showing you that there is this. Also, there is like to me at least, coming from statistical mechanics or more the machine learning side of the problem, there is a slight how can I say, a slight theoretical problem, which is that I basically used also a lambda CDM is present in the calibration and also in the validation I'm showing you. So it's very present, it's a little bit too present. So somehow I'm like saying, okay, this is something I want to fit very well. I want to be sure that I will fit it very well. But this is this is done on purpose, because this is the focus, the main focus of that. If someone would wanted to do a proper universal fit of how of models, I think then you should take into account also the thing that you are saying. So if you want to say, I want to understand properly the deviation with respect to this, and do an extensive study, definitely you're right. You're right.
The goal here was to say how distant we are from CDM, because I mean, something that with Quasars we have already stated. I mean, we have another model and stuff. And so the question was, okay, but if we want now non-parametric way, model independent way to give a quantity of how distant we are from CDM, this was the goal. So that's why everything is referred to lambda CDM. Of course, we do the same work or
yeah. The goal were also to say, first of all, WZ is not the proper quantity. So if you try to fit the Hubble diagram and then retrieve WZ, you get lots of instabilities. Still, I mean, this was I think the first very difficult stuff, because as you were saying, like, it looks strange. I mean, there is a one-to-one correspondence between I of Z and W. How can it be so difficult? But I think that if I remember correctly, because this is something that we have done like lots of time ago, if you compute the derivative starting from DLL to going up to the WZ, you get like instability due to your hyperparameter. So you can still figure out where the problem is, but still numerically it's terrible. I don't know if there have been some kind of attempts towards removing this problem. So basically, with the conventional procedure, trying to improve this chart here or not, this is something I don't know. But again, according to us, you should really think in another way. Due to first of all, you should check the mathematical problem behind, and then understand the rest. Okay. thank you very much.